Okay. Now I'm gonna stop and you can take the screen, Omar.
Could you enable screen sharing?
Oh yeah, sorry. Got it. Okay, all participants should be able to do that now.
All
Okay.
right, perfect. Okay. Okay. Is my screen visible?
It is. Yep.
Okay.
Yep. Yep.
Okay, perfect. Hello everyone. My name is Omar. My proposal today will be on photon counting CT, specifically in relation to integrating detector CT or quote unquote conventional CT, which is the most popular method, a novel approach to computed tomography. So this is my overall outline for the proposal. I will be discussing what is CT, the principles of computed tomography, and then I'll be going in depth on both photon counting and energy integrating. What are they? What are their differences? Um, what, why are they used? And then I will be going into the project goals of what I want to do for the final result and how I want to bring together all these different CT modalities and to see which one is the superior version or which one is better used in different contexts. And of course, the bibliography for any cited sources. So CT is short for computed tomography. It is in essence a very popular modality in not just cardiovascular imaging, but throughout the whole body. And it's used by archaeologists to look into, uh, rolled up Greek scrolls that have been at the bottom of the Mediterranean for 2 millennia, just so they wouldn't like destroy anything. It's a very powerful way of looking at the insides of things without cracking them open. And the way it works is you have a gantry that spins very fast around a patient or the object that is desired to be imaged with an X-ray beam shooting photons through the subject with a detector on the other side to detect photon signals. And of course, those signals then become processed either through electronics, whether they be digital or analog filters, and then these signals are processed using mathematical algorithms, most popular of which are filtered back projection and iterative reconstruction, in order to get X-ray slices at each point of the subject or to recreate an overall 3D image. So photon counting CT is a specific form of CT that utilizes basically utilizes solid state semiconductors to detect the energies of specific photons. So a photon would come in, hit the high voltage semiconductor, creating an electron pair, and that electron pair will create a very, very fast but also high magnitude current pulse, which then gets converted into a voltage pulse, whether through a voltage converter in the electronics of the CT machine, and then it is then processed. And if these photons they can exceed certain energy levels, whether it be 40 keV, 60 keV, 100 keV, and they're put in energy bins and they are counted. So the entire photon energy is considered in photon counting CT, hence the name. And basically, it allows for individual photons of different energies to be counted for the overall reconstruction. As you can see, there's a image that I have that shows just the process. So A is the side view. You can see the X-rays coming in. There's collimator blades in between to prevent X-rays from I believe causing a low resolution image. And we see the high voltage is applied at the cathode and the pixelated anodes of the semiconductor. A popular semiconductor used in photon counting is cadmium telluride. And then we see in B the top-down view that shows how it's looking. This is basically the POV of the X-ray photon going into the semiconductor. Now, how is this different from energy integrating? So energy integrating also uses solid state physics, but in a different sense. So the photon counting, uh, it uses semiconductors so that the photons create a pulse, some sort of current pulse, and each different pulse, the entire energy is considered. But for an energy integrating, most integrating detectors use a scintillator. So a scintillator or a scintillating material is a material that, when exposed or when incident upon, is a some sort of radioactive beam. It generates light, and for a energy integrating CT, you have a layer of, in this instance, it's TiO2. I'm sorry, it is a scintillator that receives X-rays, light is generated, and then there are photodiodes at the ends of the material that then detect that light. And then just like previously, an electron hole pair is created, which creates a pulse, which is then processed through electronics into a computer, and then the image is reconstructed. So the actual magnitude of the energy is proportional to the energy of the photon. So it doesn't take individual photon energies, rather it integrates the entirety of energy overall, from the photons that are incident upon the scintillator. Um, so there are some key differences here. So I will go more in depth on this for the final, but we can see two examples of a lung scan. We see an A was used, an energy integrating detector with a scintillation solid state electronics, and then B is utilizing a photon counter. And immediately we could see improved CNR at lower radiation dose. And so the idea is that CT counting is a probably superior form of CT measurement, due to the fact that it does take into account every single individual photon, as opposed to the overall energy of photons from an energy integrating CT. Here's one more image um, of the carotid artery. We see that on the left side we have a conventional in this paper is energy integrating, while on the right side we have a photon counting CT, and we do see better spatial resolution just off the top. Uh, but I'd love to actually go further in depth into the actual mathematical basis and the actual technology that allows such better spatial resolution and better fidelity and lower radiation dose in CT photon counting, which goes into our project goals. So the project is primarily a deep dive to explore the technology of photon counting as well as energy integrating, though the latter would be a bit more difficult since there are multiple types of energy integrating. There's not just one single type. And the theory of operations of both. And in the subsection, I show just different things I'd like to get into, such as the material science. Why is it cadmium telluride instead of some other type of semiconductor, like something that you would see in an IC chip, like gallium arsenide. The signal conditioning, how is the signal processing actually done after the incident beams? What kind of electronics are we doing? Is it the same type of integration? Is it the same type of amplification? The mathematical foundations, as well as how the image is actually being reconstructed from the energy, from the red energy signals. I'd like to compare these two. I'd like to see in the literature how photon counting CT fares in comparison to energy integrating. What is the spatial resolution, contrast, or artifacts more prevalent in one or the other? And I'd like to explain these concepts in a uh, much more illustrative way by showing visuals, like I did in the previous two slides, showing some examples with a lung scan as well as a heart scan. Sorry, carotid arterial scan. And then I would consider maybe using some sort of MATLAB simulation to better explain photon counting concepts, or just overall the concepts covered in either energy integrating or photon counting CT, in order to better illustrate. I would have to consider what I'd want to show, maybe show the mathematics using MATLAB, showing possible reconstruction techniques. But overall, the goal is to be like a very, very concentrated analysis of the technologies of both types, and why we would want to use one versus the other, either in clinical or in research settings. So here's the bibliography, and that concludes my presentation, and I can open the Zoom call to questions or comments.
Okay, great. Any questions initially from Other students? No, not so much. Okay. That's, this is where CT is going in the next 10 to 20 years. You'll see more and more of these photon counting machines. And I agree, it's sort of precise knowledge of what the technology actually is and how it differs from what we're doing now is terrific. Um, so one of the concepts that you didn't mention that you may want to include is also the effect of uh, electronic noise on energy integrating detectors versus photon counting detectors. Because one of the big steps that gets taken is that with photon counting, you have a sort of a binary impulse. You say, yep, I have detected an X-ray, and there's no random noise on that. Whereas with the integrator, it gives you a certain pulse size, and there's always random electronic noise on that. So as you go down to the noise floor, so really ultra low dose, there's a big difference in the noise model for those two things. So you want to put that probably on your point form list there. Um, and then do you have any potential directions for the MATLAB simulation? So have you thought about what that simulation would look like, or are there things in the literature where they show different, mathematical simulations of the two techniques?
Primarily, besides just seeing like actual X-ray reconstruction, what they usually show is just energy diagrams
Yeah,
of both energy integrating and photon counting. I was thinking maybe I could do something with that with the simulation just to like explain it
yeah,
in a better way rather than just, okay, I found one out of paper and then I'm just going to put it on my presentation and explain it. That'd be the worst case scenario, but hopefully I could definitely cook something up to kind of explain that why, what is one energy diagram different from the other? What does that
right.
mean, especially with the noise floor, as you mentioned?
Yeah, I think you possibly could make a very, sort of toy scanner, like toy
Mhm.
problem scanner that has the fundamental differences of the two detection techniques, and the ability of the photon counting system also to make the localization of the detection much better, right? So basically they can cut their detector size down such that it's quite small and still get a sufficient number of counts, right? Because we can go down to a low count number. And so that could be in the simulation as well as just like what happens when I actually make many more detectors? And if you make a test pattern, how does that test pattern change? As we go in that direction. So that would also be good. Also for the collimator, just one comment is that when you have those sepia, they're called those things, and you see photons coming straight in, the principal thing that is doing is eliminating photons that are scattered. So if I have a photon come into my patient and it comes out at an angle, right? So it's a lower energy photon now because it's done this scattering, and it goes at an angle towards my detector. If it hits the detector assumes it came from a vertical position, but it didn't. It came from over there. And this scatter, this there is a penumbra, like the patient is basically shining with scattered photons, right? And so you want to get rid of those photons if possible. Much like the same way, if you take just any old light and you put it on your thumb and you shine light through your thumb, you get an image of what's in there, but everything's scattered a billion times before it gets out, so it's very, very blurry, right? So same deal with X-rays. That's great. Okay, look forward to it. Um, any any burning questions from other students? Any on that? Okay, Omar, thanks very much.
You.
Yushwan, do you want to go next?
Yeah, sure. Let
Perfect.
me share my screen. Uh, All right. So my project is, or my proposed project is a microcalcification detection with CT while accounting for coronary motion. So I would like to give a bit of background information on the CT and micro CT. So CTS is as what we have learned is a large spinning X-ray machine. But there is also another format of this called micro CT, which is a tabletop scanner, where as opposed to clinical CT where the scanner spins, in micro CT the sample spins. Uh, and the benefit to this is that micro CT has a micron scale resolution as opposed to what typically is millimeter scale resolution for clinical CTs. This is important for this is interesting for calcification detections because when you have micron scale resolution, what happens is for pixel detections that is in fact of one structure, it will eventually, or when you scan it at micron scale resolution, you will get what is more than likely to be a group of separated pixels as opposed to one blob as you would see in a regular CT. So when this is approached, image processing techniques is needed to treat it such that you're able to detect it as a singular calcification structure as opposed to if you just uh, did regular particle detection, it will show up as multiple detections for every one structure. So my proposed process is to first, because my project is to adapt this to coronary motion, is to first understand existing methods of accounting for coronary motion and use that to understand how best to simulate some kind of coronary motion and create simulations of different motions with virtual phantoms. Then I will run a virtual CT on these virtual phantoms such that I am able to adapt image processing techniques to fix the motion that is received from these scans. And finally, I will use the adaptation of these results to real life data sets in the real CT scans and refine the process to account for certain uncertainties such as noise. So largely, my proposed process is to create a series of images that is a relatively slow motion since CT scans are very fast, but it would be a large series of very slightly different images that is distributed to different CT slices in the scan. Obviously, the diagram here is exaggerated. And as each slice is slightly different, when we reconstruct the slice, it will create a different image from the static scan. And using what we know is the ground truth, which is the static scan, we can then reverse fix what is the motion distorted image based on our known ground truth. And as of right now, I have largely three ideas of how best to simulate the motion, which is towards the center, away from the center, and some sort of random motion. And ideally, after everything is adapted, this is able to use a real image and be able to label every calcified structure that is in the image and detect the various points of interest. That is the end.
Okay, cool. Yeah, I think this is a really obviously very important topic because coronaries never stop moving, even when you know cardiac gait to the QRS of the ECG and everything. When you look at the heart, if you're trying to image things down on like a 0.5 millimeter spatial scale, the heart is usually drifting a little bit, even at phases where you would traditionally say that the heart is stationary. Because we can image at such a high resolution, it's never really stationary at that resolution, right? Like all the way down to a 0.5 millimeter. So this affects in your model when you're going to do this simulation, and you're asking like, what types of motion do I need to simulate? You have to think, okay, what is the motion of the coronary during the 160 milliseconds that is required to take my data, right? So over 160 milliseconds, that's only like 1/7 of a second or something. The heart isn't going to move a long way. So I don't think you really have to worry about like random motion like this, right? Because that's just not going to happen. It doesn't have enough time to, go up and down and back and stuff. So complex motion like that is probably something you're not that concerned with. What you are concerned with is like a drift, right? And you could just calculate what are velocities, in diastasis of the heart, and like how much drift do I really need to take into account here? I agree, perhaps the drift, in different directions can give you different artifacts, like drift in the slice direction versus drift in the imaging plane where the gantry is rotating around. So those are 2 points. This is a fun project in that you get to make your own theoretical picture, right? You can, if you want, take an image such as the one you've got there, although this is a maximum intensity projection, you probably just want a slice image or a few slices, and you can take something like that and then actually digitally make that thing move, right? So over the course of, say, 150 milliseconds of submotion, you move the image itself. You take those data that have moved and you make your basically raw data for each one of those positions, and then you temporally sample your raw data to simulate the actual sampling at different views of a motion, right? So you can create very accurate models of what the motion is going to do to the picture, and then very accurate models of what do I need to do to raw data to get rid of that motion artifact at that point, right? Sometimes you can get rid of motion artifact at one place, but it'll introduce motion artifact at another place, right? Because they're not all moving at the same velocity. But the other thing you might consider is a more advanced and interesting topic is coronary artery characteristics. So quantitative estimates of what is how much low attenuation plaque, how much mixed plaque, and how much calcium do I estimate in a lesion during motion. So instead of just looking at calcium, which is a pretty simple thing, and you just need to detect whether it's there or not, to decide if something is, as we discussed in lecture, if something is low attenuation plaque, you have to estimate the Hounsfield units in there. And so that's a trickier problem. So we could talk sometime if you want about creating an ideal picture that has a vessel with different components, and then you move that and see how it changes the Hounsfield units for those different components. That would be like an advanced step from just doing calcium, but you could use the same motion model.
Okay, I will look to improve this proposal.
Okay, cool. All right, let's move on. Ari, do you want to go next?
Yeah, can you hear me?
Yes, I can.
Okay, let's see. Share screen. See if we can do this. Did it work?
Got it.
Okay. So hi, my name is Ari, and my project proposal is on scar imaging in echocardiography, and especially focusing on quantifying cardiovascular calcification. Does this work? Sorry, the Zoom thing is
Sometimes you
in.
put your mouse in yeah, now click on the left button on your mouse. That might advance your slides. There you go.
Okay, thank you. So to start with my presentation, I want to talk real quick what cardiovascular calcification is. So cardiovascular calcification is the buildup of calcium deposit in the cardiovascular system, which includes vessels and heart valves, and depends on their location. It could be a key marker for many cardiovascular diseases, including subclinical atherosclerosis, which is a thickening and hardening of arteries caused by wax-like built-up plaque, consists of mostly fatty tissues and calcium, and they could develop into small vessels and then could bleed into the vessels, then could bleed into the plaques, which could later on, usually people who have that will have severe cardiovascular issues later on. So that's why identifying these sort of problems could help to prevent, if you identify it early on, could help prevent severe cardiovascular disease events like stroke or ischemia. So on the right here is a photo of what a cardiovascular calcification would look like. Specifically in this one, it shows a aortic valve calcification, which is pointed by arrow. You can see that in the ultrasound image, it shows up as especially bright spots. And so besides using image analysis, the primary assessing risk for the pro sorry, I got nervous. The primary way of assessing for risk for risk for stroke and ischemia for severe myocardial infarction are multiple different score charts currently, and they use parameters such as age, gender, cholesterol, whether you have diabetes or not, to see if you're in high risk of having a stroke or a heart failure in the next 10 years. The problem with these sort of tools is that they are primarily influenced by ages. So someone who are very young, who show signs of having heart issues later on might get classified into a low risk group, whereas someone who's much older might automatically get classified into someone who has as a high risk group. It's not working. Okay, here. So that's why using image analysis helps provide a much more objective measuring metrics in classifying. They will help for people who are at the edge of the risk groups. It's valuable to use these sort of metrics to reclassify them. So one way of detecting cardiovascular classification would be echocardiography or ultrasound imaging, which is a diagnostic technique that uses high frequency sound waves to create images of the heart. So the transducer, as explained in the class, emits a short pulses of ultrasound waves into the body, which then travel through tissues and reflect back to the transducer when they encounter boundaries between different tissues or structures. And then the transducer acts as a receiver and detects the reflected sound waves or the echoes and convert them back to electrical signals. The ultrasound machines then process the received signals and create real-time image, and the time it takes for the echo to return to the transducer is then used to calculate the distance of the reflecting structures, which allow for the creations of the images, the slices of the heart. So, oh, well, in that case, that would be the two-dimensional imaging will create the slices of the heart. And so then it can be used to evaluate size, shape, motions, and functions of the heart chambers. And this non-invasive, it's relatively inexpensive. It's radiation-free compared to other type of imaging techniques. So one of the limitation for using ultrasound to detect cardiovascular calcification is that there are no standard method currently. It really heavily depends on the technician's technique, and it's mostly semi-quantitative, where because they just simply look for brighter spots that indicates problems, and then it's qualitative rather than quantitative a lot of time. And on the right side here is a picture of again, another picture of that shows calcification just because it looks brighter on the screen, simply because it looks brighter on screen. So, oh, here's more limitations. Yeah, so their measurements are relative, the more qualitative than quantitative most of the time. And another thing is that you might have difficulties differentiate between calcification and fibrosis, which is, no, sorry, valve sclerosis, which is natural thickening and stiffening of the heart valve due to getting old or other chronic conditions. They might then evolve into calcification, which is the scarring might evolve into calcification, which is much more serious, but it's hard to tell that on ultrasound. They might have different brightness, but they are just all bright a lot of time. So there is an effort to put into quantifying the ultrasound images rather than just looking at the qualitative characteristics. So two of the more recent efforts of trying to make this happen. One of it is to use calibrated integrated backscatter, which means the reflection, sorry, which relies on trying to sums up the intensity of the reflected signals over a specific region and average it over a defined area, but it doesn't really provide a feasible, it's not really feasible in routine clinical practice, and study has shown that there's a lack of correlation between the integrated backscatter measurements and other methods for assessing fibrosis. And also, again, there is a lot of variability in equipment, patient condition, and the operator technique. So it's not really reliable in the clinical sense. And so another method that people have been trying to use to quantify echocardiography would be post-cancellation echocardiography, which uses, well, not always, but often uses a method called post-inversion, and involves transmitting two ultrasound pulses in rapid successions, with the second pulse being inverted version of the first one. And when they encounter linear tissues, usually more healthy tissues, then the reflected signals from the two pulses will cancel each other out, and which means the overall signal showing up will be reduced, whereas nonlinear tissues, tissues with fibrosis, tissues with calcification will reflect the inverted pulses differently. That will result in enhancing harmonic signals that stands out. So the as pulses travel through the heart, they interact with various tissues. So healthy myocardium, healthy heart tissues respond similarly to both pulses, so they cancel out. But nonlinear tissues, so calcified fibrotic area, respond differently. So then there's less cancellation, and a lot of time instead enhances through harmonic signals. So Oh, did I skip something? You know, I didn't. So one technique they've been using to do pulse to mm, so sorry. This is just a continuation of what I said earlier. On the right, you can see a two-chamber view, and that's using a E-scar, which I think is just a preset that one of the studies use for that use a pulse cancellation technique that enhances the that can enhance the difference. And so most of the this is a two-chamber, so the top this is the can you see my mouse? Sure. This is well, the top part is the LV, and then the left ventricle, and the left bottom part is the left atrium, and most of it is healthy, so it doesn't really show up on the scan, but you can see the especially bright spot pointed by the error that indicates scarring tissues. And so this is a more quantitative way of comparing quantitative assessment comparing to traditional method, which is just, oh, there is a especially bright spot compared to the neighbors. However, there's a lot more clinical trials that needs to be performed before this becomes more reliable. And so my project proposal would be to explore the physics behind the pulse cancellation echocardiography and its clinical applications, since there are a lot more studies coming out that shows clinical applications detecting specific diseases based on it. And so the literature review component would just focus on understanding the underlying mechanisms and reviewing clinical studies of applications, and especially this presets called eScar. I found a lot of papers on it, and they look pretty promising, as in pretty useful in clinical applications specifically. And then the simulation component would be either using MATLAB or Python. I haven't decided which one yet, but my thought would be to generate a ultrasound wave and try to model it how it might propagate through the tissues, and then see that if I can reproduce the scenario where there's a nonlinear response or versus there's a linear response, and see that if the technique can to see how effective it is to enhance the final result. And my goal would be to get better understanding or insight into the effectiveness of this technique. And then here are my references so far. And that concludes my presentation. Thank you.
Okay, terrific. So the simulation would be would you use the literature and the current physics understanding of how this eScar technique works to generate equations that you would then, do basically plots of how you get these different reflections on the inverted wave for different examples? Or would it be a simulation that goes down to a sort of a physics level of actually simulating an ultrasound wave?
I was planning to do both, probably start with existing mathematical model that exists out there. I
Yeah.
listed some here. Oh, I didn't list it out, dang. Well, the bubble oscillations and some of the equations mentioned in class, I probably start there first. And then if I can, I would like to delve into actually simulating the ultrasound waves and see how they interact with each other.
Okay, that's cool. And the eScar, I'm assuming, is like a certain vendor has this technique. Is that right? And they call
Yeah,
it.
I think it stands for echocardiography. It's for detecting scarring tissues.
Yeah, yeah. So you probably want to go to their website, and wherever, if they have white pages, sometimes they publish technical reports on these new imaging techniques. And it's a good place to start finding all the references. Although it looks like you're well along your way for a good bibliography and a lot of references for this. So that's great. Terrific. Well, this will be interesting. It's something it's new to me, so that'll be great. You know, and in terms of finding different physical properties, not just in calcium, but in other tissues, it would have great value.
Okay,
Cool.
thank you.
Thanks, Ari. All right. We're gonna Jerry, do you want to go next?
Yeah, sure.
Thanks.
You guys can see this all right?
Yes.
8%. Okay. Oh. And hello, I'm Jerry. And today I will be talking about my project proposal, which is to reduce noise of cardiac CT scans using neural networks. So background, currently the most commonly used methods involve iterative reconstruction, which is where you assume some final data set with either statistical or geometric models, and then you can back project. Sorry, this is for CT. Back project, and then you can compare the raw data of the actual picture with your model picture. Do some sort of gradient descent or optimization to bring those two closer, and then you forward project again, and you can repeat until you have a model with potentially like ideal statistics, which is in other words reduced noise. This, and of course sometimes I think you can reduce artifacts as well. I think this is from there's a dental scan. There's like a metal filling somewhere on the side, and if you model it properly, you can remove that when you do the reconstruction. Deep learning. Studies have shown that deep learning produces superior results to. Oh, sorry. Okay. Studies have shown that deep learning produces superior results to iterative reconstruction. For example, you can see here there's some streaking visible in the iterative reconstruction, but deep learning managed to sort of learn these inherent properties of the system and remove this streaking. I think in terms of speed and computational cost, it can be faster or similar or often faster than iterative reconstruction. And this method is, I think, I don't know if it's commercially used, but at least it's been FDA approved starting in 2019 from GE. And I believe Siemens and Philips also have their own models that are FDA approved as well. A little bit of background on deep learning. I think I mentioned it before. Deep learning usually refers to, it refers to a neural network with a lot of hidden layers in between, which ideally enables you to learn more complex patterns. And briefly, the way a neural network works is that you have some sort of input data, and then in between each of these nodes is sort of like a neuron, where you have various one-dimensional inputs that are fed in. Well, actually, I think they could be multi-dimensional as well. But fed in, they have, and there's a summation function. And then this activation function is, I think, sort of similar to a neuron. And it has to be, usually it's non-linear, so that you can learn sort of non-linear patterns as you go through this network. Interesting. Oh, and eventually, as you get your output, there usually be some sort of cost function. Like you say, oh, my output didn't match this input of like, sorry, for example, you give it a noisy image and then it'll have this output, and then you compare it to an ideal clean image, and then you can sort of compare the differences, the costs, and then you will sort of backpropagate go back and I adjust these weights accordingly to minimize this difference between the output and the ideal image. And through this, you can learn, like I said, different patterns, complex patterns, nonlinear functions, things that might not be easily like mathematically modeled from iterative reconstruction. My goal here is to compare these deep learning and iterative reconstruction approaches using models that are freely available online. For example, Google TensorFlow has an auto-encoder model which can be used to reduce noise. This is and I believe I found various iterative reconstruction models are also available online for free. And briefly, this autoencoder model usually, at least in the Google version, reduces this data to a lower dimension, which is known as an undercomplete model. And this forces it to sort of learn general patterns instead of like specific just images. So the plan is to write training on iteratively reconstructed data, sort of learn the general patterns, and then I will test it on previously unseen like raw CT scans with the noise still present. Ideally, I will ask people with experience in the field, such as Professor McVeigh, to sort of judge if the quality is actually improved or it's actually clinically useful. And if I have time, I plan to explore potential hybrid models, such as, for example, if the input data is first filtered, or maybe it's partially reconstructed, and then you feed it to a machine learning model. But that's a stretch if I have time. I believe that's all. Those are my references. I suppose if there's any questions, feel free to ask right now.
Okay, any questions from the group? Okay, I mean, this is a good project. It's straightforward. You'll get you come out of it, with a good example of writing a pipeline, sort of a neural net, whether it's a CNN or whatever you choose to use. You can obviously make your own noisy raw data. Like you can produce a whole set of images that what their ideal look is, and then you take them into the raw data space, add noise over there, right? And then train a network on many instances to perform CT reconstruction on that noisy data, given the fact that you have the underlying truth because you made the image. It's a little harder maybe if we do that with if you try and train on clinical images, because we need to get a lot of them together to do that kind of training. But there are, I know online, students in previous years have found sources of many, many CT images online, right, that you can use for this. Is there a sort of overriding hypothesis that you have? Are you going to have a essentially model-based reconstruction versus the deep learning, or is it going to be standard, filtered back projection versus the deep learning? What will be the final sort of output that you'll evaluate?
Yeah, I think my point is ideally, I compare like sort of this model reconstruction. For example, this Tiger model that's available on GitHub with the autoencoder output.
Okay.
I'm not necessarily think like my results might not be better with this like simple available the simple model that's available online. Because but I think all of the actual FDA approved ones are sort of secretive about how they actually go about things.
Yes, they are. Yeah.
And even the papers that I found, like usually they'll use the FDA approved models, but like they don't really have an insight into like how it actually works.
No, that
So
a lot of the clinical papers that have compared image quality, for example, have no understanding of what is in the box, right? What's in the black box. They just use it. And I think your instinct is right that they probably are hybrid techniques. They could be like the deep learning could be employed at any phase, like for noise reduction in the raw data. It could make filtered raw data, right? Or noise reduction even in the image after reconstruction, right? So nobody tells you how they actually do it. They just say it's deep learning,
right,
right?
So
So yeah, it gives you the opportunity to actually create a network that you know how it works, and then you can evaluate its performance on images that you have created, right? So that's the benefit of doing it this way.
yeah. So hopefully I'll learn a little bit of what helps actually
Right.
produce a good result with machine learning. Yeah.
Right. And so I think you also want to define what you're going to say is a good result. And I wouldn't just count on the experience of myself looking at one picture and then the other and saying, I like this one on the left better. You probably want to propose to do some measurements like sharpness of edges, contrast to noise,
Hmm.
perhaps have a test phantom that from that test phantom, you can easily determine the modulation transfer function, things like that.
Okay. Okay.
Some quantitative metrics as well as just looking at it and saying this one's better than that one. Okay,
Okay. Sounds good.
cool. Thanks. That will be interesting. So now, who hasn't gone yet is uh, Frank.
Sure.
So did you got the data, I'm assuming?
Yeah, but the biggest one I just cannot unzip it. So,
Oh, okay.
but I think I got the rest of it. But I probably just gonna double check with you to see which is which.
Yeah.
I
Okay.
got the Dicom. Dicom works no problem. I open them all.
Yeah.
Yeah, they all look good.
So after class, then we can quickly go over that, like where's the data is and how I need to repack it. Okay.
Sure, no problem.
Okay, cool.
Can you see my screen?
Yes.
All right. So my name is Chen Li, and my project is about the beam hardening correction for the cardiovascular CT. So I will cover what is beam hardening and what effects or what artifacts it has on the real CT scan. And I will cover another two methods, like two potential methods to correct the beam hardening, which is line fit, and I will also try to do the derivative reconstruction. But before we move on to what is beam hardening, we need to know something called air normalization. This is done in basically every CT scan. Because when we get whatever the raw data sinogram, we have to do the negative log of the intensity over the intensity of the air scan. Because the CT attenuation is flipped. Like for example, the bone, it's gonna absorb the most number of the photons. So your detector actually will detect a very small number and a very low energy photons. So it turns out it will be very dim or very dark on the CT image. But this is not right. Like if we take a look at the real CT scan, the bone looks very, very bright. The bone is like probably the brightest. That's because we use this negative sign over here to flip the attenuation. So here's the example. On the left is the correct one. This is like air normalized. And if you don't do the normalization, just use the raw data to reconstruct, you will get the image on the right, which looks pretty bad. Like you cannot do anything. It's not helpful diagnosis. So it's like not helpful at all. So We're gonna do normalization and the attenuation flip on the CT image. Then we can move on to the beam hardening. So this is a geometry of a real CT machine. So this is like a fan beam, and you get your gantry rotating around the patients, and this thing emitting out the X-ray and it penetrate the patient's body. And all your detector here is just gonna count the number of photons after it going through the human body. And for the X-ray or X-ray beam coming out of the CT machine usually is the polyenergetic beam. I mean, I think it's doable to do like a monoenergetic, but I heard it's like very, very expensive to do. So most of the time it's the polyenergetic. So no matter what KeV value or KeV range you want to use, your X-ray energy is always a distribution. So across the whole spectrum, it cannot be a single peak. So because this property, when you're actually going through the many different tissues, the tissue gonna block the low energy photons. So what's gonna happen is on the right. I mean, this is a very simplified the way to say it, but it's a good example. So when you're going through more tissue, the more low energy photons gonna be blocked. So they're gonna be gone. So this is gonna cause your average X-ray energy going higher and higher as you're getting deeper and deeper into your human body. So this will cause the energy pretty high and it will look really bright on the detector. But as I mentioned in the previous slide, the attenuation flip. So instead, it's gonna look very dark. So this is the beam hardening artifacts. And this is the example. This is the water phantom we scanned last quarter. So this is nothing but a chunk of water. So it's a uniform material. So this absolutely doesn't look right because it's just water, nothing else but water. So ideally, they should have the same color everywhere and also the same value everywhere. So this thing should have like uniformly the same color. But it's because it's beam hardened, so it doesn't look right. So here's another example of the beam hardening artifacts with a different KeV value. So this one's like low KeV, and this one's like a high KeV. So as you can see, the higher the energy X-ray goes up, so actually your beam hardening is kind of reduced. So at the very bottom is like a cross section. So if you draw a straight line across this water phantom, what do you get is this? So you can see at the center, you can see some dents. So it's going down, which is not correct. So what we should do is we should correct this thing to make it into a uniform object. So what do we usually do? One way we can do is we can capture like one column of the sinogram. So this is the sinogram of the water phantom I just showed in the previous slides. So you will get like one projection. So basically one column of the sinogram is the projected from one angle. So you will get a projection right here. Then you can try to correct it. So this is the way to correct it. So the dotted line is like with the beam hardened, but I need to correct it up into the ideal projection. But this way is not really doable because I don't know how to do it because that's a curve thing and you don't know where you should go. So what do we need to do? We need to do some geometry as a circle. So what do we got here in the x-axis is the detector channel. That's basically your detector positions on the CT machine. So which corresponds to the distance D. And we can figure out the radius of this circular phantom. That's not hard to do. So we can figure out the R, figure out the D. When we do some geometry, we can figure out this distance T. This is attenuation thickness. This is what we actually care about because this is the distance through which the X-ray is traveling. Then we can plot this thickness against the attenuation to generate a new plot, which is going to look like this. So usually for the polyenergetic, you will get this curve kind of like not linear, but it's more like a exponential, I would say, which is not correct. So this thing should be linear because we want to be a uniform across the different like a depth or different thickness across the of the tissue. So one way we can do is we can do the line fit. We can try to fit the line for the raw data and try to fit another like perfect linear line of what we want to be. Then just drag this curve down or push it up to correct it. So if you do this like perfectly, this is what you should get. I mean, this is like really, really good. This is like generated by the GE machine, by the General Electric CT machine. This is like a perfect, literally perfect. So if you draw like a cross line across the center of the circle, you can see they're very, very uniform across the whole phantom. There's absolutely no dent at the center. So this is the one way to do it. Then we can move on to the cardiovascular. So this is a cardiovascular skin. What I'm gonna do, I think I'm gonna treat this thing as a circle too, because the field of view of this thing is also a circle. So I will treat this thing as a circular phantom, but with like non-uniform material inside. So if I have, but that's going to be a pretty complicated problem. If I have my beam right here, let's assume this is a parallel beam. So if I have my beam going through my heart like this, like at the center one, you can see the beam actually going through many, many different tissues. It's going through the ribs, so that's bones. And these might be like air that would go through the myocardium. Then it goes through your spine, which is also bone, and you get the projection at the bottom. So this is actually pretty complicated. Like, so I'm like the way, like the method I'm thinking to start with, I would do the segmentation first because I need to know where exactly each tissue located at. Then I probably can capture the attenuation across the whole, every single column of the whole sinogram to know where the bone is. So for example, this one, maybe I cross like 10 pixels of the bones and like 20 pixels of the air and maybe like 100 or like 1,000 pixels of the heart muscle. So I will try to like deal with like the attenuation of each tissue separately. So I will create more than one of this thickness against attenuation plot and I try to correct it. I'm not even sure this is going to work or not, but this could be a goal I'm trying to reach, trying to achieve. Then another way is the algebraic iterative reconstruction, which is called ARC. I mean, this is also basically exactly the same thing as Francisco mentioned in his lecture. So you can use this thing to keep iterated and to compare with the ground truth plot, try to reconstruct the image out of the sinogram. This is also from his lecture. So this is the ground truth, and as like the more times you iterate, the better result gonna be. But I look into the code. In the demonstration they used is not like it doesn't have any beam hardening. The sinogram they use is basically a radon transform of a ground truth image. So it doesn't have any beam hardening. So what I'm trying to do is we're gonna try to implement this iterative algorithm. And I will use the beam hardened raw data to see how well this thing can work to remove the beam hardening artifacts. So that's my goal. I mean, first I will try to do the line fit like we did in the last quarter. So this is going to be like a continuity from the project we did the last quarter. Then I will see the performance of this algebraic iterative reconstruction algorithm to see how well it works too on the beam hardening sinograms. And that's it. Here's my reference.
Okay, that's cool. Are you now the data that we've given you, are you going to use that data to calculate these line integrals?
I think so.
Yeah, okay. So the first thing you're going to want to do actually is reconstruct those raw data just using a normal filtered back projection, but reconstruct the whole field of view so that you can do those integrals through the whole torso, right? So because the images that that usually get reconstructed, and they're the ones that were included with the data, are a partial field of view. They're sort of zoomed in to the chest, and so they won't have the ability to visualize what the heck is on the outside of that field of view. So you're going to want to reconstruct them just to get the basic, the whole field of view scan, right, in order to get an accurate line integral.
Okay.
Okay. Otherwise, I think you're set. I think it should be good. I'm not sure how much beam hardening artifact will be evident in those images. Like maybe we want to talk about where does GE correct their data for beam hardening? Is it already corrected in the raw data that we've given you? Is the basic question, right? So
Oh, I mean, I guess it's not, I guess.
I guess I don't know. So, but we can discuss that.
Yeah,
Okay.
I didn't like try to reconstruct the raw data yet. I
Yeah.
probably can try it today.
Yeah, that'll be good fun. Okay, great. Okay, so let's move on. And who else do we have? Oh, Michael, I guess Michael, you're the last person, right?
Yes.
Okay, terrific.
Do you see my screen?
Yes.
So for my my name is Michael Nguyen, and for my student proposal, I decided to do photon counting CT versus conventional energy integrating detector CT. So for my table of contents, I plan to go over my introduction, my research objective, my research methodology, and the expected results. So for the introduction of photon counting CT, so photon counting CT is an innovative CT technology that utilizes a direct conversion X-ray detector. So pretty much it directly records incident X-ray photon energies as electronic signals, and then pretty much it utilizes semiconductor materials in order to generate electronic signals from the incident X-ray photons. So for the schematic on the right, it pretty much represents the process of photon counting CT, in which it uses a semiconductor to directly generate positive and negative charges. And with the negative charges, they directly go to pixelated anodes to record each individual photon along with its energy, which produces the electronic signals. And then for the introduction of the conventional energy integrating detector CT, pretty much the process for that is a conversion of X-ray photon energy into electrical signals through a multi-step process. So pretty much the process is with scintillators. They're materials that emit light when exposed to X-ray photons, which then is utilized to generate visible light when interacting with X-ray photons. So then the generated light that we get is then converted into electrical signals using the photodiodes. So with this schematic on the right, we basically use a scintillator to generate visible light. So when an incident X-ray photon hits it, then pretty much the light is recorded by a photodiode with reflectors in between detector elements to basically reduce the crosstalk. And pretty much my research objective is to pretty much identify the fundamental differences pertaining between photon counting CT and conventional energy integrating detector CT. I plan to evaluate the expected improvements of using photon counting CT, along with assessing the clinical implications of photon counting CT. And then for my research methodology, I plan to go through a literature review. So I plan to explore the photon counting CT, conventional energy integrating detector CT, along with a comparison between the two. I plan to also do a data collection. So pretty much for my data collection, I plan to utilize imaging data from patient scans using both CT scanners. I plan to cover image quality, dose levels, and other parameters in my data collection. And then with the data collection, I do plan to gather experimental results, and then along with the research papers and articles I do end up finding. And then for my analysis techniques, I plan to use calculated data such as like mean, standard deviation, raw data values. And obviously with that, it would be dependent on my findings in my own research. And with that, it would just be, like I mentioned, utilizing comparative research methods and statistical analysis. And then with my expected results, I plan to hopefully find enhanced spatial resolution and image quality in photon counting CT and compare the differences between the photon counting CT and the energy integrating detector CT. I then plan to find reduced radiation dose along with improved dose efficiency in photon counting CT, and along with hopefully, finding artifact reduction in photon counting CT scans as well. And then these are some of my references that I've used so far. And then that's pretty much all I have for the time being. But thank you.
Okay, great. Thanks, Michael. So for both you and Omar, the other thing that occurs to me that you might want to look at is when you read articles about photon counting CT, they're usually written by people who have just obtained it or have been working on it for a long time. And they very rarely highlight some of the things that can go wrong. So you might want to also spend a little bit of time, describing what can fail with photon counting CT. Primarily what held the field back for a number of years was essentially you could saturate the detectors. They couldn't work fast enough. And so you would have X-ray upon X-ray piling up on the detectors, and you'd get erroneous results. Now, if you look up piling up artifact or something like that, that might give you a couple of papers on that.
Okay.
Okay. Well, it looks like everybody's in good shape. And I'm looking forward to the projects. So any other questions up to now? I will put another problem set now that you've done this and it's behind you. You can put another problem set online. And we'll keep going on Monday. I think we're going to keep going Monday with some more CT applications. And before we move into MR, cardiac MR. Okay, any other questions or anything?
I mean, I may want to discuss the data set a little bit.
Yes. Okay, terrific. So just stay online for a second and then we can discuss it quickly. Yeah. Okay. Everyone else good?
I guess for me too, I was curious if you know the names of like where I could get data or
Right. Let me, one of the teams now, the data that you need, basically, do you want raw data to be turned into images or images to be denoised?
I think ideally just raw data, and then maybe I could denoise it myself. Or,
Yeah.
although if it happened to be denoised also, that'd be nice, but it's not a must.
Yeah, let's talk about that. I think in terms of training, because you're going to need a number of examples, right? if I gave you like 10 images or something and 10 raw data sets, which is easy for us to get, getting 1,000 is not easy, right? So you may want to train by creating your own data. So you have a picture, you take its, radon transform to make the raw data, and then you add noise to that data to make it realistic raw data. And then you know what the image was to start with, like the noise-free image to start with. And so you have the ground truth and you can train on that, right? So you train the thing to essentially do a radon transform on noisy data or on data that has missing views. Like you can take a radon transform that has 10 times the resolution that you could sample. You subsample it to make it realistic data, and then you see what the image is that you train on that. So you go back to the ground truth image on your subsampled data, right? And that's what the network learns to do, right? Or you could focus on the network learning how to see through noise by adding random noise and training it to see through that random noise. Okay. So those are the two things that I would recommend. Is like, then you're in total control of what aspect of the data you're getting the network to look through, right? Whether it's subsampling or high noise, right? And then, so you get your network working, and then we could take raw data from a human scan and put it in your network and see what it produces, right? But I'm not sure we can give you enough images to train on that, because you need
Yeah.
probably need 1,000, right? Something like that, or maybe at least
Yeah.
500 or 400 or something.
Okay.
Okay.
Okay. Also, I guess, do you know if there's any nicer deep learning models online, or
I'm sure there is.
I'll just have to search for it? Okay. Okay.
Oh, if you go, into GitHub or something like that, I'm pretty sure there is. And
Okay.
what I would
I'll
do
look
is,
around.
yeah, go back and look at the presentations from last year, the projects. I'm pretty sure somebody did this last year. I can go back and look too, and point you to it if it's there. Okay, but I'm pretty sure one team did this either last year or the year before. So I'll go.
Okay.
Yeah.
Okay.
Okay. So
All
shoot
right.
me
Thank
an
you.
email to remind me if I don't get back to you right away. Just say, hey, you said you were going to go look for this project.
Okay.
Okay, great. So Chan, I think Francisco made some mat files that had the central slice. So they're much, much smaller now, right? The raw data was huge before, but
Yep.
now they're much smaller. So if I go to the drive and go into courses, is this where it is? Where did we put it? No, I didn't put it on courses. I put it in share folder, right? Yeah, here it is.
Yeah, I think so.
Yeah.
Wait, I'm just wondering, like the meta file
Mhm.
Francisco made,
Yeah.
those are the raw data for the cardiovascular scan, right?
Yeah, they are not the raw data for the air scans.
But like I'm just kind of confused because, for example, for data set of 41005,
Yeah.
if I open the DICOM, there are at least like 800 images inside, but like the raw data is just like one file. So I guess it corresponds to only like one image, right?
No, the raw data is actually pretty complex. It corresponds to all of the slices that were sampled during the raw data acquisition. So remember, you have the detector is 256 slices by 832 pixels.
Mm-hmm.
And so a raw data file is that dimension sampled thousands and thousands of times.
Oh, okay.
Right.
Okay.
So the program that Francisco used, he extracted the central slice from that data. So he had 256 slices in the raw data file. He subtracted out the central slice and put it in this central scale data. Now, is the central scale data, let me download it quickly and see.
Yeah, I'm just kind of confused.
Yeah, I know.
What he gave me.
I'm getting a little confused too. So let's work it out right now. First, let me share my screen, okay?
Sure.
And so here, what I've done is this data here, central scale data. Have you downloaded that?
Yes, I downloaded it unzipped on my desktop already. So
Okay,
they're like 1, 2, 3, 4, 5, 6.
okay, so I'm gonna open it here. And it is,
Yeah, 15 mat files. Yep.
okay, so this number here, this 41009, that is a scan ID number. And so the 005, 6, 7, and 9, these four, those are clinical data. Okay, so
Okay.
those are scans of a person.
Okay.
And that's raw data. It might be from 2 slices. Let's take a look. I'm gonna start up MATLAB. We'll drag it in there and see what it looks like.
I mean, the DICOM file you gave me, there are 41005 too. But if
Yeah.
you open that 41005,
Yeah.
there are 3 sets. One is called a calcium score Acer V50. Okay. One's calcium score STD-AX.
Yeah.
And one is calcium score thin.
Yeah. So those are just different reconstructions of the same raw data.
Yeah, but if you open like each folder, each
Mhm.
one has 256 slices.
Yes, it does. And so the raw data will correspond to slice 128.
Okay, that makes sense. That's what I'm at.
Yeah.
That's what I want to know. Thank you.
Yeah, sure.
Okay, because
Yeah.
I was so confused. Like, why there only one raw data?
Sorry about that. Okay, so I'm going to drag one of these map files. They're 4 megabytes. Let's drag one into here. Is that okay? So it has central data, MA. Yeah, so the central data is 832 by 2 by 1039. Okay. And so
So
what that means is
I
if we,
guess it's 120 and 129 slice. I guess the 120 and 129 images. I guess.
it has one slice, which is this number.
Mm-hmm.
It has 832 detectors, okay? And it has, the sinogram has 1039 angles.
Yeah, that makes sense. Yes, that
Okay.
makes sense.
All right. So if we could plot a sinogram by saying plot central data. Okay, we're gonna do the first one. Everybody will do 1, and then the second one, everybody, right?
Yeah, you need to squeeze it.
Oh yeah, you gotta squeeze it.
Yeah.
To squeeze the, so I put squeeze in front of central data,
Yes, and include the central data.
this, like so.
Yep, try it.
No. Oh,
Oh, ZE.
yeah. Yeah, I did that. Okay, there we go. Okay, so it plotted all 10,000 of those. 832.
Oh, should I use like I am show
Yeah,
instead
that's
of
what
the
I should
plot?
do. So I'm gonna do, yeah, you're right. It's a image SC, I think should be better.
Yeah, that should work too.
Oops. Shite. There you go.
Yep.
Okay. So these values, let me bring it out here. Let's ask what are the actual values. So these are the RGB values here, 0.8. Looks like they're 0.239, 0.73.
I think this is like non-normalized sine of
Yes, this has not got the air data yet, right?
Yeah. Uh-huh.
So this is normalized by Francisco to be relative numbers, right? 18. So the index here is the photon counts, is proportional to
Mhm.
photon counts, this index here, right?
Mm-hmm.
Okay, and then the really high counts up here, that must be air or something here, right? That's 304,000 right there.
Yeah.
So yeah, so you need to normalize this to the air scan.
Sure, I will.
Okay. And then, oh, this is interesting. Let's plot that. Plot MA. This is over the 1,039 projections.
Mm-hmm.
This is what the MA or the current is during those projections.
Sure.
Okay, so there's only this set, you have a constant set of projections, and that goes from, who is this? From like x equals 360 to 677. So that's what's that, 300 projections?
Yeah, I guess so.
Yeah. And so interestingly, this is why I did the air scan with exactly the same protocol,
Mm-hmm.
is so that this will be the same in the air scan, right?
Okay.
This envelope, right? Probably not ideal to have it like this, like only 300 central views at the central MA.
I mean, I feel like 300 might be like a too short sinogram, to be honest.
Yeah, yeah,
I may just use the whole thing and then use this MA to scale in the
exactly.
normalization. I think that's what I'm gonna do.
Yeah, exactly. Okay, and then I think, yeah, he gave you also these ones, these are air scans. So the latest air scans like this, let me clear everything.
Oh, that's the air scan? Okay.
Yeah,
Okay,
the
okay,
ones
okay.
with the big numbers are the air scans. So after 9, so 13, all of these are different air scans, right?
Oh, okay.
That I took on Sunday morning or something. So let's look at this one. So it's the same,
Mm-hmm.
right? We can plot, let's just, oops.
Yeah, it's slightly bigger, but
It
I
is
don't think
bigger, right?
yeah, but I don't think it will be uh
Why is that bigger? I don't know why it's bigger.
I mean I can do this. I can go through every single air scan he gave me. This is until I find a good one.
No, but I'm not, that one should be a good one. Let me, um, what was the other one, was Image SC, right?
Yep.
So that's the air scan.
Yeah, that's the air scan. Yep.
Yeah. Okay, cool. And then so it ramps up, stays constant, ramps down. Any of these columns give you an estimate of the air scan. So the average across here is the air scan value, right?
Yes.
Okay. Cool. So that was at a high MA. And then I also made some scans. So this is actually exactly the protocol, probably. So now let's plot MA again. No, it's still the same. Bigger. Huh. What happened? 202. Okay. It's exactly the same, just a lower MA.
Okay.
Yeah. So you can use either one, doesn't matter.
Sure,
I just
sure.
wanted to make sure that I did a bunch of lower MAs. I did a bunch of them so you could average them together. But when you look at them, you really only need one, right? Because you can average all of these things together
Yes.
in that direction, and so it should be fine. Okay, cool.
Yeah, so I don't need to worry about the biggest file in your drive, right?
No,
I
no.
guess that's like what Francisco already processed for me.
Exactly. He processed all these so that you have these 5 mega. It's very nice. They're single slice or
That's
two
nice.
slice.
That's sweet. That's sweet. So all I needed, I just used the whatever DICOM file in the like
Yeah.
41001, whatever, use as the ground truth.
Exactly.
Okay, sweet.
Okay.
All right.
All right,
Thank you
man.
so much. Thank you so much.
Okay, good luck.
Yep. You have a great day.
You too. Bye.
Bye.